Okay, so in this presentation, we're going to go over some examples of definite integrals. And in this first example, we're being asked to evaluate the definite integral to find the area of the shaded region. So we see that our shaded region starts at x equals 1 and goes to x equals e. The top of our shaded region is bound by the function f of x equals 1 over x, and the bottom is the x-axis, also known as y equals 0. So we can say the area is equal to the definite integral from 1 to e of 1 over x dx. And we know the definite integral is the natural log of the absolute value of x. And we still have to evaluate it at the bounds from 1 to e. And by the fundamental theorem of calculus, we plug in the top bound, and then we subtract the result when we plug in the bottom bound. Log of e is 1, and natural log of 1 is 0. So this area is equal to 1. So we wrote a definite integral representative of the shaded region. We found the antiderivative, used the fundamental theorem of calculus, and evaluated. In this next example, we're being asked to draw the shaded region, and we see that we have an absolute value graph, which we know that absolute value graphs are V-shaped, and we want to find the vertex of it. And if we take this expression, 2x minus 1, and set it equal to 0, we get x equals to 1/2, and that is where this absolute value graph will change direction. We see our lower bound is at 0, so if we plug 0 into the x, we get 2 times 0 minus 1, which is negative 1, but the absolute value of negative 1 is 1. So this is the first branch of our absolute value graph. We see that the upper bound goes to 2, so when we plug 2 into x, we get 2 times 2 minus 1 is 3. The absolute value of 3 is 3. This is the second branch of our absolute value graph. And now the left and right bounds and the bottom bound, and we have our shaded region. And the problem asks that we use geometric formulas. So this first triangle here, again, area of a triangle is 1/2 base times height. We see that the base is 1/2, so it's 1/2 times 1/2, and the height is 1. So this first triangle has an area of 1/4. This second triangle has an area of 1/2 times 3/2 times 3. So the area is 9/4. So the total area is 1/4 plus 9/4 equal to 10/4, or 2.5. So we can say that the definite integral from 0 to 2 of the absolute value of 2x minus 1 dx is equal to 2.5. In this next example, we have a polynomial function that we need to graph. And we see that it's a parabola shift down 3 units. So if I plug 0 in for x, we see that we would get -3 as the y-coordinate. Next, I'm going to look at my lower bound of -1. If I plug -1 into x, -1 squared is 1, minus 3 is -2. So we see we have the ordered pair -1, -2. And I can make a table of values here. And I'm just picking values until I get to my upper bound of 3. So 2 squared is 4, minus 3 is 1. And 3 squared is 9, minus 3 is 6. And we have our parabola graph. And now we have to make the bounds with the x-axis. And we see that we have a negative region because it's below the x-axis and a positive region which is above. It looks like the negative region is larger, so we expect to get a negative answer from this definite integral. So the antiderivative of x squared minus 3 is 1/3 x cubed minus 3x, and then we keep our bounds of integration. We plug them in using the fundamental theorem of calculus. Plug in the top bound first. So this is our f of b minus, plug in the bottom bound next. This is minus our f of a. And we see 3 cubed is 27, divided by 3 is 9. Minus 3 times 3, so it's minus 9. Negative 1 cubed is negative 1 times 1/3 is negative 1/3. And negative 3 times negative 1 gives us plus 3. So we see that 9 minus 9 is 0. And negative 1/3 plus 3 is 2 2/3, but we're subtracting that. So our final answer is negative 2 2/3. We expected a negative answer because we saw the negative region was larger, so this makes sense with our observations. Finally, this last example, we have two of them to look at. We see that they do not give us any function definition. We are solving this strictly using geometry. So here we see that there is a rectangle, and the rectangle has a height of 6 and a width of 2. So the rectangle area is 12. And we need to take away the semicircle from it. So the area of the semicircle is 1/2 pi r squared. The half means half the area of the circle. We see that we have a radius equal to 1. So the area of the semicircle is going to be pi over 2. So we're going to subtract semicircle equal to pi over 2. So the total area equals 12 minus pi over 2. That's the exact answer. You can plug into a calculator to get a decimal approximation. And now if we look at the second example, we're going to cut this up into shapes that we can find the area of. This first one is a rectangle with height of 3, and we see we have 1, 2, 3, 4, 5, a length of 5. So this rectangle has an area of 15. These triangles we're just going to approximate. We're not going to find the exact intersects here. But if we take here a base of 1/2 and a height of 3, we can say that this triangle has an area of 1/2 times 1/2 times 3. So it has an area of 3/4. And this triangle, we'll say the area is 1/2. We'll say the base is 2 and the height is 2. So it has an area of 2. And this trapezoid, we'll say, has a base of 2.5 and a base of 2. So a trapezoid has an area which is 1/2 the sum of the bases times the height. So we'll say 1/2 times 2 plus 2.5, and we see the height is 1. That gives us 1/2 times 4.5, which is 2.25. So the total area is going to be 15. Because this triangle is under the x-axis, we need to make it negative. So we'll say, I'm sorry, this one's positive. This one's still above the x-axis. So 15 plus 3/4. This next triangle was under the x-axis, so minus 2. And this trapezoid was above, so plus 2.25. And if we add all of that together, we get 18 minus 2 is 16. And this is an approximation, and it's an approximation because we did not find the exact location of these intersections. We just approximated them. Example A is exact because we used exact coordinates. Example B was a little more tedious. We just used approximate coordinates. So I hope that these examples worked out will be helpful for you in completing your assignments. Email me with any questions or if you need any help or additional examples.